All right. Good evening, everyone. So looks like we don't have any audience here today for the live session. That's all right. Uh, Thanks, Krishna Kumar, for joining. Um, so probably what we will do is I will just quickly go through a question I have today. It's about turbojet engines. It's basically the big three content that you covered in your lectures. Um, and also Mm, so this, I think a similar kind of question is being asked in your assignments too. So I hope this would be helpful for you. So let's get quickly, let's quickly get started. Let me check my recordings once. Okay. All right. So in week three, there are different things that we covered in the lectures. The main is the week three purely deals with turbojet engines, and there are different configurations of turbojet engines that we are familiar with. One is single spool and two spool, uh, and then we also saw uh, how each of the performance parameters varies with respect to different design variables. For example, pressure ratios, turbine entry temperatures, Mach number, mass flow rate, all these things is how are these affecting thrust, TSFC, uh, efficiencies, also specific thrust, right? So um, that is what we quickly that is what we covered in the week three lectures. So let me just quickly give you an idea about uh, the turbojet engines. Mm, Give me a minute. Okay. So this is a typical turbojet engine, a single spool turbojet engine. And our question today is also going to be single spool turbojet engine. So we all know there's going to be an inlet, uh, and then there will be a there will be a inlet or diffuser duct, which gets the air, which sucks the air in, and then it gets compressed in the compressor, and then it goes through the combustion chamber where gets mixed with the fuel and then starts burning, and then it produces very hot gases, and the hot gases with high pressure, since it got compressed, gets expanded in the turbine, and then once it goes after that it goes through a jet pipe. It's just a simple pipe, and then it goes through the nozzle where it gets accelerated. Okay, it gets accelerated to high velocities. So the nozzle is for acceleration of the gases. That is the main reason for this nozzle, and basically because of the expansion of gases is what's going to happen. Okay, so this is a typical turbojet engine. And we say single spool because the compressor has to be driven by a turbine, and the turbine and compressor are in the same spool. So when we say dual spool, we will have two, low pressure and high pressure compressor, and low pressure turbine and high pressure turbine. And when the low pressure turbine drives the low pressure compressor, it will be in one spool, and uh, high pressure turbine and high pressure compressor will be in another spool. So it will be a constant. Is just spool is nothing but this connection between the compressor and turbine. So it will be like a concentric cylinders, hollow cylinders on one over the other. If you have two spool, if it is a single spool, it will be a one solid cylinder. Okay. This is a turbojet engine, a typical turbojet engine. Now, if I want to plot it in the TS diagram, we are interested in thermodynamic, uh, you know, properties of this engine, or we are interested in what is the uh, different station pressures and temperatures at different stations. Okay, so we are plotting a TS diagram for this, and this blue color line we have here is a P infinity line. It's a constant pressure line, So you will see multiple constant pressure lines in a TS diagram. And this infinity line is the ambient condition. It represents ambient condition, ambient pressure basically. And then what we have is we first, the air gets compressed, you can say, from infinity to 2. If it is in the ground condition, this is important. If it is in the ground, it doesn't really get compressed while it goes through the diffuser. It doesn't get diffused. But if it is in a flying condition, it gets compressed to a little bit higher value pressure P02, and then it undergoes a further compression in compressor. Okay, so from 0 to 2 is there will be a temperature increase and also a pressure increase from infinity to 2, uh, that happens in the inlet or diffuser. And then we have compressor. From 2 to 3 we have compressor, during which further compression happens from P02 to P03. Now, uh, at the end of the compressor, we will have a high pressure, which is P3 or P03. And when the pressure ratio across the compressor will be P03 by P02. Okay. So this will be the high pressure in your in your entire gas turbine engine. Okay. And also, but this does not correspond to high temperature. You will see soon. Now, once it leaves the compressor, it enters the combustion chamber. In the combustion chamber, we are adding the fuel, so it's a ideally it should be a constant pressure heat addition, but because of various reasons losses can happen, so the P03 will not be equal to P04. So 3 to 4 is the combustion chamber, and during this process pressure will almost remain constant, or in fact pressure will be slightly dropping because of losses. uh, but this T4 will be the highest temperature that you will reach in your turbine. So in your entire gas turbine engine, the highest pressure will be in the compressor exit, and your higher temperature will be at the turbine inlet. Okay. And after the combustion chamber, we have turbine, which expands the air from 4 to 5, and from 5 to 6 we have jet pipe or tail pipe. Uh, that is just a connection between turbine to nozzle. During this process, there will be a small pressure losses. That is what we are model. That is what we have here, and we see it's a straight line. That's because it's an adiabatic uh, process from 5 to 6. When the flow goes from exit of the turbine to the inlet of the nozzle, we can assume that it's an adiabatic process. That's why you see a straight line. Temperature doesn't change. Okay. And once it in the nozzle, it further gets expands to 6 to 9, and this 9, the data point 9, can either lie at P infinity or it cannot. When it can lie or when it cannot, that I will let you think about it. We will again address this by the end of this session. Okay, so this is the overall TS diagram. The actual cycle will follow the red line, uh, but the ideal cycle would be isentropic process for compression and isentropic process for expansion, which is ideal. So you will see a straight line. So these black lines are actually straight lines. It represents ideal cycle, or ideal process between two stations. Okay, so but we are interested in actual process, so we'll be doing actual processes. Okay, let's quickly jump into the numericals that we have here, and let's try to compute what they are asking for. So what they have is, I have a small turbojet engine with a compressor pressure ratio of 8. Okay, and the turbine inlet temperature of 1200 Kelvin. They have given mass flow rate also. Mass flow rate is 15 kg per second. When the aircraft is flying at 260 meters per second at an altitude of 700 meters. So it is flying at an altitude of 700 meters with a speed of 260 meters per second, which means the air is going to enter the engine with the speed of 260 meters per second. So that's the thing. And also the mass flow rate of air is 15 kg per second. So what they have asked is calculate the propelling nozzle required, the net thrust developed, and the TSFC. Okay, the so in order to get the nozzle area, thrust, and TSFC, we have to go through all the processes uh, happens inside the turbine, gas turbine. We need to find all the station properties, then only we'll be able to end up getting the parameters that they are asking for. So in addition, they are also given certain efficiencies for intake. The isentropic efficiency for intake is zero point 0.9, and for the compressor is 0.88, and for the turbine is 0.92, and for the nozzle at the end of the turbine is gas turbine engine is 0.95. Um and then we see that we note that there will be pressure losses in the uh, combustion chamber and the tailpipe. So here the combustion chamber pressure loss is 6% of the compressor delivery pressure. Okay, and combustion chamber efficiency is 0.98. They didn't give pressure loss for tailpipe. Maybe we can for now we can assume to be 100%. I mean, sorry, 0%. There won't be any pressure loss. It will be same. We can assume that. Uh, and at an altitude of 700 meters, we have T infinity to be 242.7 Kelvin, P infinity to be 41.06 kilopascal, and the added to the heat added during the uh, you know in the combustion chamber is the heating value of this fuel that we are using is 43 thousand, I mean 43,000 kilojoules per kg. Okay, so let's quickly note down the given. So givens are, as I said, V infinity, M infinity, uh, and the pressure ratio is given, turbine entry temperature is given, heating value, and ambient conditions are given. And the next is we also note that there are efficiencies and losses, and also we are assuming certain things about the gases properties. So the specific heat ratio of air which is entering is 1.4, and the specific heat ratio of hot gases which comes out of the combustion chamber would be 1.3. Okay, and also corresponding Cp and Cph we are assuming for this question. Now what we need to find is, as I said, we need to find the exit area of the nozzle, thrust, and then TSFC. Okay, let's go forward. So if I want to quickly draw an idea about how do we solve this problem, uh, here, so what we know is initially we know T infinity and P infinity. Also we know the speed at which the aircraft is flying. We know inlet which has a efficiency of 0.9, and then after the inlet we can find the pressure P02 and T02, and using that P02 and T02 we can find the compressor uh, uh, station properties. So compressor inlet will be P02 and T02, and the pressure ratio is already given. So with this we can find P03 and T03, which is exit of the compressor. And after the compressor we have combustion chamber whose pressure losses are given and also the efficiencies are given. In addition, you can also, at the end of the combustor, we know its temperature, max temperature we can reach is 1200 Kelvin, which means we cannot add more fuel, or we cannot go beyond that. So we are asked to find out fuel air ratio for this case. Okay, so we are going to find fuel air ratio, which is F, and also we can find the exit pressure of the combustion chamber. Once you find the combustion chamber, the next component that we have is turbine, whose efficiency is 0.92, and then from turbine you can get exit pressure and exit temperature. Now the tailpipe we have here is it has no losses. That is what we have found. Okay, so the tailpipe has no losses. It's been given in the question. So because of this, there won't be any change in properties across the tailpipe. And then we have nozzle. From nozzle we can find P9, T9, and V9. Okay, so you must have noticed that I have uh, colored certain things as green, which, so these things are required to find the area of the nozzle, thrust, and TSFC. That's why I so this green are like ultimate goal that we need to find out, and the red are intermediary uh, things that we need to find out. Okay, now let's go component wise. So here I have a simple turbojet engine that's just for a reference in the bottom corner, and also its corresponding TS graph. So the inlet is, as I said, we have three things at the inlet. We just need to find out T02 and T02. So we all know the equation for T02. So you must have noticed that there is no efficiency because we are going to inlet is basically most of the time uh, for a flying aircraft or flying turbojet engines, it's adiabatic process. So that's why we no need to worry about it. You can assume that it's adiabatic process and you can find it. So this equation is actually coming from isentropic flow relations that we already know. Only thing we need to find out is we need to find out m infinity. Now m infinity is the Mach number at which flight is moving, right? What the question has given is v infinity. Velocity is 268 meters per second. So we know how to calculate m infinity, which is nothing but v infinity by speed of sound. Uh, and the speed of sound is gamma rt, right? So if you substitute all these values, you will be able to get m infinity. So if you have calculator, can you quickly find out? So 268 meters per second is the velocity. Uh, so Tushar is asking, can we get recording of this meeting regarding revision study? Yes, Tushar. So usually what I will do is once the meeting is over, I will be posting the recordings in the YouTube. I will be updating in a sheet, which I think you should be able to access from your NPTEL portal. If you go into your NPTEL portal, the final link will be problem solving session. So if you open that, there will be link to the Google Sheet where I will be putting my videos. Basically, I will give you the links. So you don't need to worry about it. Okay. But I highly recommend you to attend the class if your time permits, if your timetable matches, because it will be a lively interaction, and also if you have any questions, you can uh, ask. Yeah, thanks Tusha. All right. I hope that cleared your doubt. So we can find the m infinity from this relation. So if you do the calculations, so it might come around 0.858. Okay, so you can check my calculations. Usually I make some mistakes in arithmetics, but I hope this is right. Okay, so the Mach number with which the flight is moving is 0.858, and which means the air entering the jet engine is 0.858. Okay, so now if you substitute this 0.858 here, so you will get the temperature at the uh, inlet to the compressor. Okay, so how much would that be? So T infinity, if you try to calculate it, so it might come around 278.4 Kelvin. Okay, all right. So and then we have P infinity here, sorry, P02 here, which is the uh, which which is nothing but the inlet to the compressor, or the pressure after the exit of the inlet. Now you might notice that there is an efficiency of the diffuser here, so which is around point 0.9, and we know P infinity to be 41.06 into 10 power 3, 41.06 kilopascal, and we just found out m infinity. So if you put these numbers, um, if you calculate it, how much would the pressure be? So it might come something like 63.47 kilopascal. Okay, so this is the pressure you will see in your engines. Okay, so all these numbers are not actually some random numbers. These are the real pressures and temperatures that we encounter inside an engine. So that is something you should keep in mind. Okay. So now that we found the pressure and temperature after the inlet, we can go forward and do the next component, which is compressor. So we know that compressor, the pressure at the inlet is 63.47 kilopascal, and we know the temperature to be 278.4 Kelvin. And the compressor has an efficiency of 0.88 and the pressure ratio is 8. So that actually directly gives you the P03, which is nothing but 8 into 63.47 kilopascal, which should be something like 507.75 kilopascal. So I'm just moving on because these are basic calculations that I'm sure that you guys can easily do it. So this is basically nothing but like around 5 bars. Okay, so this is the highest pressure that you are going to reach, that you will reach in this turbojet engine. Okay, um, and then we also need to find out temperatures. So this is 507.75 kilopascal, and then we need to find temperatures. Temperature, we can use the efficiency of compressors equation, um, and we know how the efficiency we obtained. So if you have any doubts, you can stop me anytime and ask. So I'm just going forward because we already assuming that we already know the equations. Okay. um so if you rearrange this, so basically this is the tau z. We wanted to, tau z is nothing but T03 by T02. Maybe I will write down somewhere over here. So tau z is T03 by T02. So we are interested in getting T03. So now if I just rearrange this, so it will be something like 1 plus pi c power gamma c minus 1. So here I put c because the air which is entering is a cold air. So, and we will have gamma, we should take air's specific heat ratio. That's why we have gamma c. And then if you substitute all these relations over here, you will end up having, how much would this be? So 8 power 0.4 by 1. So it might come something like 1.922. Please check if I made any mistakes. So if this is 1.922, then we already know T02, which is nothing but 278.4 Kelvin. You just substitute it here. So if you substitute, what happens? It comes something like 535.1 Kelvin. Okay. So this is the compressor exit pressure and temperature. All these are stagnation pressures and temperatures. Okay, please note that. And moving forward, the next component is combustor. And in the combustor, we already know pressures. Pressures entering the combustor is 507.75 kilopascals. And also the temperature is 535.1 Kelvin. This is the pressure and temperature of gases entering the combustor, and in that fuel gets mixed and then it burns and then it produces hot gases. We are asked, we should find only the pressure because the compressor exit temperature and also the turbine inlet temperature both are same, which is given, which is 1200 Kelvin, right? So instead we need to find what is the amount of fuel I need to add to reach the 1200 Kelvin. So that is the thing we need to find out. So before getting into it, let's find out the pressure at the exit of the combustor. Okay, so how do we find out? We have given the pressure losses for the combustor, which is around 6% of the compressor exit pressure. Okay, so just that's why I wrote It has 0.06. This is 6% of the P03. Now, if you just rearrange this equation, P03 would be equal to something like this. So it would be something like 0.94 times P03 we already know, which is 507.75 kilopascal, right? And how much would this be? So it will be little less than 507.75 kilopascal. So it might come around 477.3 kilopascal. All right. What will be the percentage of moisture at combustor? Okay, good question. So the percentage of moisture. So it depends upon your fuel burn rate. Or you what you can say the type of fuel will determine the temperature determines. So if you think about it, moisture is nothing but H2O. Isn't that what you're talking, Tushar? When you say moisture, it's H2O, right? Or okay, okay. So this H2O is actually it can be a product of combustion. It can also be coming from the air. Yeah, air also will have some content of moisture. Air will have some moisture. So this air plus H2O will enter, but this percentage would be very less. We all know it might be something like 0.1% in air probably. And that also I'm talking in terms of higher altitudes. So based on atmosphere, we will come to know what is the amount of percentage of moisture, what will be entering the combustor. But what also happens is we are adding fuel. So in the fuel, usually fuels are kerosene. Okay, right. Okay, very good. So this is will be like 2/3 percentage. So which will be like 0.6 kind of percentage, right? Okay. Now in the combustion chamber, we'll have fuel is white kerosene. So kerosene would be something like C10H20 or 20 something something will be there. Okay, it's a hydrocarbon fuel. When it combusts with air which has oxygen in it, plus nitrogen and plus water vapor. So what it does is it also produces H2O, CO2, CO, and all the products. In this amount of H2O, so actually when it enters maybe 2/3 percentage, but when it goes out, it will be more than 2/3 percentage. And the amount of H2O present in your exit of the combustor depends upon various things. One is oxidizer to fuel ratio or air to fuel ratio. So it depends upon how much amount of fuel is present. If the air fuel ratio is less, which means less amount of fuel is being added, which means the combustor is running at lean conditions. When it is in lean condition, the production of H2 would be less. If the combustor is at stoichiometric, when it runs at stoichiometric, the production of H2O would be a little high. So comparatively, it depends upon whether air fuel ratio one number one, and also the other thing is temperature. So if the temperature is very high, this H2O molecule does not remain as a H2O molecule. It can decompose and become H and OH. Okay, it can become H2 and O2. So all these things can happen. So all these things will determine whether your H2O, whether the H2O's moisture content at the exit of the combustor is, these things determine your moisture content. So that is why afterburner is attached on some engine. So afterburner is actually attached not not because to reduce moisture content. Is that your question? Is the moisture content um, because of moisture content are we adding afterburner? Is that your question? You can feel free to unmute yourself if you want. That's why after.
Yes, sir. For producing high thrust over there,
Hmm.
that's why it is required. Is it required over there?
Right. So just because of high thrust only that we need afterburner, its moisture content is not really the reason.
Okay, okay.
So moisture content we are fine with it, moisture content. So all yeah. Um, although this H2O is going to come out anyway in after the combustion. So even if the afterburner is there, when the combustion happens there also, your H2O is there. The output of the combustion is actually H2O and CO2 in ideal cases. So H2O concentration will always be there. So we do not want, and also you can see the moisture in terms of liquid is a little bad, but usually as a steam it is fine. It is still a gas, right? So the
But
temperatures here
sir,
are,
sir,
yeah.
my doubt is when the moisture is present in the combustion chamber,
Mhm.
so it's also reduce the shell life of the combustion chamber, not through that.
Come again, which it also reduces?
Sir, moisture is present in the combustion chamber at some point zero 0.01, point zero 0.02,
Right, right,
like that.
right.
But it's also reduce the shell life of the combustion chamber too, no, sir? Means the
Oh,
section over there with the
mm-hmm.
combustion going on, it also reduces the combustion over this shell life of the combustion chamber.
You meant to say life of the combustion chamber? The
Yes, sir, yes, sir. Life of the combustion chamber.
ha. So, hmm. Mm, so probably I would not think so. The reason is, maybe I need to check once again. I will get back to you. The reason why I'm saying is the temperatures there are very high. So moisture in terms of liquid, there won't be much of a issue.
Yes, sir, that is true. But regarding the shell life of the engines over there, it
Mm-hmm.
will be after 2 years, they
Yeah,
will
yeah,
get.
yeah. So yeah, yeah. That happens. So this shell life, I may need to look into it, but I will get back to you about it. But it is of, but it has nothing to do with afterburner. That I'm sure about it. But about the life of combustion chamber, if the H2O concentration in the air increases, what would happen? So that is a good question. I will get back to you. Okay. All right. Any more questions? Okay. If there are no questions, yeah. Thank you, Tushar. So what we can do is we know the pressure. Now we need to find out what is the amount of fuel that we need to add in order to reach 1200 Kelvin. That is the goal, right? So basically, this is nothing but an energy balance. So we have some energy coming in with some pressure and temperature, some energy of airflow entering with some energy, and it has to leave with certain energy that is fixed. T is equal to 1200 Kelvin. Now we need to know how much amount of fuel that we need to add. So that energy balance is what we are going to do. Here you can see that this M infinity CPC T naught 3, right? This is the energy with which air enters, and M dot F eta BQR is the energy with which the fuel enters. Okay, this QR is nothing but the heating value. So here we have some heating value like 4300. So ideally this should be 43,000 kilojoules. It's not 43,800. So from the uh, you know given data. So this heating value is actually lower heating value. There are two heating values, lower heating value and upper heating value. So can you guess what would be the difference between lower heating value and higher heating value? So it actually relates to Tusha's question also. It has something to do with H2O, uh, water or steam. So whether so upon combustion, whether the if you take into account of latent heat of vaporization of water, uh, then it will be a lower heating value. If you don't take that into consideration, then it will be a higher heating value. So basically, if you think of it like this, so now upon combustion, the fuel gets burned and then it produces H2O and CO2. Now, if you just leave H2O, once it burns, we have H. H2O will be in a gaseous state because the temperatures would be very high. So if you consider that state, if you see the energy difference between these two, when it's inlet to the outlet, then you will have lower energy release because your H2O is in uh, gaseous state. Now, if you cool down your gases, combustion products to a uh, lower value, such that all the H2O gets converted to uh, liquid form, then upon fusion there will be some energy release. So if you add that energy release, that will be uh, considered as an higher heating value. So that way higher heating value number would be a little larger than 43,000 kilojoules per kg. But uh, that is actually used for some other purposes. In our case, for aircrafts and even for other diesel engines or petrol engines, we always use lower heating values. Okay, because our combustion products, we are not condensing it later. At a later point, we are not condensing it. So we will be using the lower heating value. Okay, so think about it: lower heating value and higher heating value. Why are we using it? What is the difference? Okay, so coming back to the energy balance, the energy with which the air enters is the first uh, term in your equation. The second term is energy with which your he, fuel is entering, and which will be equal to the total energy coming out of the combustor. So it's just simple. So energy in is just budgeting. You need to do the need to budget the energy. So, so these two are inlets. This is an outlet. Okay, and you must have noticed that I'm using CPH here. The reason I'm using CPH is upon combustion, since you have all these gases H2O, CO2, CO, your composition of the air will not be same as air at the exit of the combustor. It will have H2O, CO2, CO, and all the different varieties of products. And because of that, your specific heat ratio and also your specific heat, constant pressure specific heat, will not be same as air. So it will be different. So that's why we have CPH and CPC. Okay, so I hope you understood the spirit of why we use CPH. Okay, now we can rearrange this to find out F is nothing but m dot infinity by m dot F. These equations you already know, and if you substitute everything here, so T03 is nothing but 535.1 Kelvin. So if you substitute all these things here, please mind the what do you call the units of the QR. So usually people miss that. So it's 43,000 kilojoules per kg. So you need to put 43,000 into 10 power 3. Okay. So once you substitute all this, if you find out what is the fuel air ratio, it might come something like 0.0209. Please verify this if you have a calculator with you. And yeah, so this is the amount of fuel air ratio that we are including. Okay, the next component we have is turbine. From turbine, what we are getting out is the work from the turbine is what we are getting out. And the inlet is, you have the high temperature gases which gets expanded in the turbine. So flow work getting converted into a shaft work in turbine. So we need to find out what is the work done, or this work done will provide us what is the pressure and temperature at the exit of the turbine. Okay, so we'll see how is that. So again, for the turbine, we need to do energy balance. The reason why we do energy balance in the, so we must not have done this for both for compressor or other things, uh, inlet, or we didn't do much of energy balance because the energy conversion things are happening only in the combustor and the turbine. Okay, from turbine we are giving the work to the compressor. Okay, so that's why we do energy balance in these three regions. In fact, we do energy balance everywhere. This isentropic flow relation is also kind of an uh, energy equation if you think about it. I will let you uh, just explore that. How did you get the isentropic flow relations, and what is this stagnation properties? All these things, if you think about it, everything comes down to one single, uh, you know, one single principle, which is balance of energy. Okay, so it's a give it a thought. Okay, let's come back to the turbine. So in turbine, we can do energy balance. The energy balance is going to be, we are going to run the turbine for, when we are going to run the compressor with the turbine work. So um, the work done by the turbine would be this part, which will be m dot infinity into 1 plus f. I added because we added fuel also in previously in the combustion chamber. So what enters the turbine is m dot infinity into 1 plus f, and it enters at T04 and leaves at T05. So that's why T04 minus T05. And this is used to drive the compressor. So that's why you have compressor m dot infinity CPC. You can note that CPC, because air is what is getting compressed in the compressor, not the gases. Okay, the gases are produced after the compressor, and it is compressor is going from 02 to 03. That's why you have T03 minus T02. And also you have something called mechanical efficiency here, lambda. For this question, they didn't give any mechanical efficiency. We are considering 100%. Okay, this mechanical efficiency is nothing but because we connected it with a shaft, there can be some losses. That's why this mechanical efficiency we need to take into account. Okay. Um, Now you just rearrange this, you will end up having this kind of equations, and then you again substitute all the values here. So what we know about P04, P04 we found out to be 477.29 kilopascal. Okay, and also T03 we found out to be, let me write it down, T03 is 535.1 Kelvin, and T02 is 278.4 Kelvin. So and F also we found out to be 0.0209. So you just substitute all this, you will end up having T05 as, so let me quickly calculate, 278.4, 278.4. So here the 1 is multiplied because the efficiency is 100%, and 1.0209 divided by 1200. Mm. So how much is T05 you are getting? So let's just find out T05 by T04. So T03 is 535.1 divided by 278.4 minus 1. This is 0.922 into 1005. Actually, I think I missed. This is CPC. CPC is 1005 and CPH is 1157. So I think I missed here. So maybe I will 1005 by 1157. So that's why I was getting some weird numbers. Anyway, into 278.4 divided by 1.0209 divided by 100, 1 minus. So it is coming out to be something like 0.818, around that. Can check, not sure. So, and also T04 is 1200. So let's say if you multiply that, it is coming out to be 981.6 Kelvin. Okay. I hope this is right. If not, no, you can find out. So basically P0, now we have found temperature. Now we also need to find pressure. The pressure, how do we find? So temperature we already found out to be 981.6 Kelvin. So pressure we know, we can find it using this relation we have from the turbine efficiency. Okay, and if you substitute all these values here, so here also 981.6 Kelvin, and you can see I'm using gamma h here. So gamma h is 1.3 basically. Okay, gamma h is 1.3, gamma c is 1.4. So these are the numbers we already assumed during the in the initial given stage. Okay, so upon substitution you will end up having P05, which would be something like 183.63 kilopascal. So it enters at higher pressure, which was around 477.29 kilopascal, and it leaves at lower pressure 183.63 kilopascal, which is expected because the flow process is converting it to mechanical work, so as a shaft work. Okay, all right. So this is about the turbine. The next is tailpipe. There is no losses, so we will just P06 will also be same as P05. We'll just write that down just for the sake of completeness. And the next would be nozzle. So here you should be little careful. So to find the pressure and temperature at the exit of the nozzle, first thing what we need to do, we need to first check whether the nozzle is choked or not. Okay, so P06 is 183.63 kilopascal, and T06 is 981.6 Kelvin. So based on whether the nozzle is choked or not, uh, the pressure and temperature at the exit will vary. Okay, and if the pressure and temperature at the exit varies, then accordingly the velocity also varies. Okay, so first thing we should do is we need to check whether the nozzle is choked or not. So for that we have the choking condition, which is P06 by PC. P06 is nothing but the inlet stagnation pressure of for the nozzle. PC is the critical pressure. Okay, so if you substitute these numbers, you will end up having something like 1.8964. Okay, you can verify these numbers. Uh, if you rearrange this, so PC would be something like P06 is 183.63 kilopascal divided by 1.8964. So the critical pressure would be something like 96.83 kilopascal. Now the question is whether this is choked or not. So for that we need to know what is the exit or the ambient pressure, right? So ambient pressure, the question gave us the ambient pressure to be 41.06 kilopascal. So it is clearly 41.06 kilopascal is actually less than 96.83 kilopascal. So which means PC is greater than P infinity. So does that mean it is chalked or unchalked? So if PC is greater than P infinity, is it choked or unchoked? So I hope what the choking condition and the reason to check choking you already know. So it just tells whether the maximum mass flow rate in a nozzle you can reach only. Uh, I mean, you can reach only a certain maximum mass flow rate in a nozzle. You cannot reach beyond that, and it is going to depend upon the inlet of the nozzle. So this choking condition will tell whether your nozzle is performing, whether the mass flow rate through your nozzle is very high or less than that. It will basically tell that. If your critical pressure is higher than the ambient pressure, then your nozzle is chocked and the mass flow rate through your nozzle is fixed. If it is not, your mass flow rate through your nozzle can vary. It can be lesser, it can be more. So that basically happens when you're in a ground condition. So when your flight is at stationary, normally your nozzle will be unchocked. And as you climb, you know, it slowly, the pressure at the inlet of the nozzle continuously keeps on increasing. And at a certain time, it will reach to a certain value, after which you will have you will have a choked nozzle at the for your in your gas turbine engine, and this doesn't happen in the ground. Once you take off, after a certain time, after a certain distance you cover, there will be choking happens. It basically depends upon the pressure of the inlet. Okay. So this critical pressure here, it is greater than P infinity here, so which means the nozzle is choked. Okay. So if the nozzle is chopped, then we all know what would be P9. P9 would be same as the critical pressure. Okay. So the critical pressure is 96.83 kilopascal. So your P9 also will be 96.83 kilopascal. So I hope why we are checking the choking condition, and also why we are, you know, find like taking y P9 to be same as critical pressure. I hope that is clear. If not, please let me know. I will be able to go in depth. Okay. So now that we know P9, let me just put it down. 96.83 kilopascal. Now we should find T9 and V9. So we know our nozzle is chocked. Okay. Let's write that down. Nozzle is chocked. And hence, if the nozzle is chocked, at the exit of the nozzle, it's going to be Mach number will be equal to 1. The reason is this is a converging nozzle. It's not a converging diverging nozzle. If it's a converging diverging nozzle, you will have a supersonic exit. Okay. At that time, it will exit will not be equal to Mach number will not be equal to 1. It will be more than 1. And in most of the commercial aircrafts, commercial jet engines, usually we will have converging nozzle. Only in fighter aircrafts we may need higher thrust and higher things. There we will have converging diverging nozzles. Okay. So basically there also we will have some kind of adjustable nozzle which can change from converging to converging diverging, and also the expansion ratio. Okay. So since we know that it's a Mach number is equal to 1, we can use isentropic flow relation. You can put Mach number equal to 1 and then you will end up having this relation. Okay. I'm not showing that calculation, but if you do this, you will end up having temperature ratio should be something like 1.15. Now T06 we already know. T06 is where is T06? We just found out. Same as T05, 981.6 Kelvin, and the pressure at the P06 would be 183.63 kilopascal. Okay. Now you can rearrange this T06 by 1.15, and hence your T9 would be something like 853.56 Kelvin. Now velocity at the exit of the nozzle is, we are writing it like this, which is nothing but the sonic speed, because we know Mach number is equal to 1 there. So that's why if you write it like this, you can put T9, you can substitute the T9 here. You will end up having 1.3 into 287 into 853.56 Kelvin. So this would be, how much would this be? So you can check this calculation. It might come something like 544.3 meters per second. Okay. Okay, we have a question here. So what is the name of coating applied to nozzle from preventing melting of the nozzle? Hmm. Good question. So, mm, usually what they do is in rockets it's simpler. I mean, it's complicated in terms of construction, but in rockets, what we use is we have cryogenic fuels. So what we will send the fuels to cool down the nozzle. Uh, in aircraft, we actually no need to do that because your temperatures here are lesser. In rockets, it's not the case. The temperatures will be like 2000, 5000 kelvins. Here, the temperatures are lesser. So we no need to cool that much. But certain, uh, you know, uh, military aircrafts, we may need to do it. Uh, but the name of the coating is something I'm also not familiar with. I will also get back to you about it. What about the nozzle? Is convergent or divergent? So nozzle can be only two ways. One can be convergent nozzle or it can be converging diverging nozzle. Okay.
No, sir. My question is in convergent or divergent nozzle over there in military aircrafts.
Mm-hmm.
So there was a coating which I already saw.
Okay.
So when the afterburner over there and temperature is so high over there,
Mm-hmm.
why do not get melting? My question is that only.
Yeah, yeah. We will get that. So that's why in military aircraft we need to do cooling. So for that we have this coating. Uh, Usually it is
It is in white color, sir. The coating was in white color,
okay, okay,
white creamish color, white
okay.
creamish color. I asked over there, but they told it is a classified.
I see.
No other didn't tell me. That's
So
why.
yeah, yeah. It might as well be classified. So, but I have to check about it. I'm also not sure what is the coating that they use. But as you said, uh, they have to do that coating. But I'm not sure what is the coating.
So the coating would be, sir, polymer matrix or a fiber.
So you usually what happens is erosion happens, right?
Yes,
Because
sir.
of gases coming out, and they have want
This
to increase the
ashes are forming over there. Ashes means chunks of the carbon over there, no? The burnt
correct,
carbon over there. It
correct.
is putting on, but nozzle over there very less.
Hmm.
So what it's there when high temperature is there, carbon settlement, carbon ashes is also there.
Hmm.
It also prevent from the settlement of the carbon ashes also.
Right.
What I want to know that how what is the thing which prevent all of these things in simple one coating over there.
Hmm. 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 Yeah. So usually, um, yeah, I'm not sure what kind of coating that they do, but maybe I will ask professor about this. Maybe he will be able to answer this better because he has better experience than me. I will ask professor and I will maybe I will share it with you in the next class. Okay.
Yeah, sure, sure.
I will, yeah. Or I can also put it in the common forum. Yeah. I will get back to you about it. Okay. The next class I will, yeah. Very good. Thanks. It's a good question. I'm also learning things.
Thank you, sir. But I'm learning from you. That's why.
All right.
Previous
Okay.
questions over there that nobody at least answer over there. At least you are some giving some responses over there.
Yeah. Sure. Anytime you can ask me questions. Okay. L- Okay. Let's move forward and complete this. We have only a few more steps to do it. So we found out the velocity also, velocity with which the it is getting out, the gases are going out. Now we found everything. So let me just put it down here. This will be 853.86 Kelvin and this will be 544.3 meters per second. Okay. All right. Now the final answer. So we need to find the area of the nozzle. So the nozzle area is we are denoting it as A9, which is basically coming from the mass flow rate relation, which we all know. M dot is rho AB. Now The rho we don't know, but we know pressure and temperature, so we can use ideal gas law. But what is the mass flow rate? This mass flow rate is going to be the total amount of mass flow rate entering the nozzle, which would be the air mass flow rate plus the fuel mass flow rate. Fuel also has already entered in the combustion chamber. So that is something you need to take into account. So then you can write the density as P9 by RT9 from ideal gas law, and then you can substitute it and rearrange this. It's the same thing, just that MF I wrote it in terms of F times M infinity. Okay, and then if you substitute it, F is nothing but 0.0209, and T9 and P9 we just found out to be 96.83 kilopascal, and T9 is 853.56 Kelvin. Okay, so and V9 also we found out to be 544.3 meters per second. So let's substitute this also. So once you substitute it, what you will get is you might get something like 0.066 meters per. Okay, this is the area that you will area of the nozzle, exit area of the nozzle. So it is not necessarily the you cannot size the whole entire engine based on this nozzle area. The inlet will be used for sizing. That will tell how big your engine is. Okay, this is just the nozzle area, but you can get the idea of around which order it is, it's been. And then the next is thrust. We all know the thrust equation. You are going to have momentum under pressure thrust, um, which is going to be m dot infinity into 1 plus f v9 minus v infinity plus p9 minus p infinity into a9. And we also know all these relations. We can just, all the numbers, you can just simply substitute it. F I already have here. If you substitute all these numbers, how much would you give? The thrust might come something like 8116 newtons. Okay, so R you can say 8.116 kilonewtons. So the why we write it in terms of kilonewton, I will let you know soon. So in TSFC, and finally we also need to find TSFC. TSFC is nothing but m dot f by t, and also again you substitute these numbers. F is 0.0209. Once you substitute these numbers, you will end up having TSFC to be 3.8627 into 10 power minus 5 kilograms per second per Newton. Okay, we can actually change this into kilograms per hour. If you want to write it in terms of kilograms per hour, what will you do? You just need to multiply it by a factor which would be, it will be 3600. Reason is in 1 hour we have 3600 seconds. That's the thing. So you can just multiply by 3600 to it, and you will end up having 1.39 kilograms per hour per Newton. So this is your thrust specific fuel consumption. Okay, so these are the questions being asked during the these are the uh, unknowns that we found out from this question. So now important thing is, one last thing that we need to revisit is this TS diagram. Okay, the reason is, we in this region, if you look at it, TS diagram, what we did was we expanded from 6 to 9 is what the nozzle is, and we expanded it till the curve which is P infinity. Okay, so this actually tells, if only this happens only if it is an unchalked nozzle, but what we have is ours is a chalked nozzle. Okay, so because of that, you will not expand till the P infinity. Instead, your pressures will be little higher. Okay, so your TS diagram would be a little different. So your final 6 to 8 would be something like this. Okay, so that is something you need to note whenever you're drawing a TS diagram. It should also include, it should have the information about this. Although I didn't draw the TS in scale, but it should be accurate in terms of station and where it lies. Okay, that is it. Do you have any questions? So that is about the turbojet engine. I think we addressed all the questions been asked. So calculate the propelling nozzle area, thrust, and
Sir, I
TSF.
have one doubt over
Yeah,
there.
yeah, sure.
The outlet in turbine,
Mm-hmm.
anything effect over there when the turbines move over there, the sides of turbines, no, sir, turbine blades are the sides over there.
Right, right.
Okay, they are correct. I mean, their blade here are also happen. It's a small amount, micron over there. So,
Mm-hmm.
my question is, what prevent over there? Because what is the composite standard of that? I want to know that. Because continuously wear tear is going on
Mm-hmm.
micron, on the millimicrons over there.
Right, right.
Over a point line, maybe here you can see one of the blades over there, it will be here also. So I want to know what is that composite standard they are looking for.
In terms of turbine blades, is it? Or
Yes, sir. Yes, sir. From blades.
okay, so
Because generally we know it's titanium alloy, but
mm-hmm.
what standards over there we don't know. Quality standards over there we don't know. They're
Mm-hmm.
not in public, not in internet, not in the books.
You will not be able to get that information uh, because of various reasons. So actually, the main thing what people are really working on what is more secretive is the material of the turbine blades. The reason is it is it so there are different things happens with the turbine blade because it is continuously rotating. It is having the vibrations and as you said, the blades will be as a like a cantilever beam, and it will continuously be uh, wear and tear will happen, displacements will happen.
Forget the movement over there, reversal and things like this. One is going forward, other is over there, right hand. Some difference will be there, some 0.1 second or something over there.
uh, can you come again? For some reason I was not
No,
able to.
no. Sir, what I'm saying that the speeds over there, little bit of difference of 0.1 second or 0.2 seconds. Two turbine blades and turbine like that. Every speed is little bit different.
Right. Speeds means what speed you are talking about?
The rotating speed, sir, rotating speed.
Right. The rotating speed in terms of RPM, is it? Or
Yes, sir. RPM. It is not similar. Every blade over there is moving. Little bit of micron seconds will give difference.
it depends upon the flexibility of your turbine blade, right?
Yes, sir. Yes. Yes.
Right. So it will be rotating at same speed. If ideally speaking, if you see the blade, all the rotating speed should be same in terms of, but the blade can undergo a deflection.
Yes, sir.
Because
Yes,
of
sir.
that, each point in a blade
Yes.
can rotate at a little bit different speed, but
Difference
it
over there.
cannot
Yes.
be entirely different. It will be like an oscillatory. So
Oscillatory.
it will be like it might, as you said, it might go up and down. It cannot be continuously high or
Yes.
continuously low,
Yes.
and
Yes.
that is the main cause of this. So since it goes up and down, it is like a continuous what do you call fatigue. It can undergo
Fatigue over there. Little
fatigue
bit of yeah.
failures.
My new microns over there. Fatigue. New
Yeah.
microns.
So what people usually go with this is there is new technology is like single. They try to develop this entire blade with a single crystal. So the crystal growth they do and try to make this entire. So they will not do any machining process for the blade. Instead, they try to grow this blade with a single crystal. So that there won't be any there won't be any crack present in the microstructure. Okay, because the crack is where everything starts. If there is a lot of fatigue, the crack will initiate the uh, break. So if a blade wants to
What will
break,
be there? One blade breakdown, then
huh,
other blade breakdown, like
so
that.
crack is a starting point to propagate. So
Yes.
if you don't have crack, your strength will be large. But the problem is if you do it like that, you will not be able to reach high temperatures. So that's why they go with alloys.
That's
uh,
why it also increases the temperature, moisture percentage over there in the combustion. And the
so
combustion is also,
right.
it's like a after Newton's third law, every reaction will equal opposite reaction.
Mm-hmm.
If going more over there, less compression is there, then vice versa, everything goes back.
Right.
And many chances over there that engine goes shuttered down over there.
Hmm.
Like,
Yeah, that is also true. So sometimes, this also can happen. The pressure can go down, and then cavitations can happen. But uh, usually, typically in a turbine blade can happen, but it is very less in gas turbine engines. But in other places where you employ turbines, there these problems are very high, and because of cavitation, it can erode your blade also. That also will happen. But it is all that is a technology, that's a materials technology that people are working on, is to develop a single crystal, make the full blade with a single crystal, and also make it withstand high temperatures. So only if you have high temperature inlet to the turbine, you can extract a lot of energy from out of it, so your engines would be more efficient. You will learn more that in upcoming weeks actually. So when you plot the performance parameters, as the turbine entry temperature increases, your fuel consumption will increase, but your thrust also will increase to a very high value. Okay, so
so
you
it will, sir, it will be different behavior we can see in turboprop engine and turbojet engine.
yeah, there is a difference. There's a difference. Turboprop, you will see a big fan rotating, but it
Yes,
is
sir.
not, the flow is not controlled,
Yes, sir.
right?
Correct.
The It is a open fan,
Open house, yes.
open
But
fan.
in turbojet
But
it
in
is
turbo,
same process goes over there, but little bit of kind of different applications.
yeah, in turbojet you do not have any fan. You just have compressor, right?
Yes, sir.
In turboprop you will have additional fan, that too at the end, but also it is not closed. But in turbofan engine, you will have a separate fan, and also you will have a controlled passage. You will have the engine includes fan plus the core part. So I think
Yes,
that
yes.
that is going to be in your week 5. It will start from week 5. So this is week 3. Week 4 we will have afterburner. So for week 4 also I have another afterburner question, which will be the same question, but we will just add afterburner and see the comparison. We will compare the performance, how big the difference is, right? Um, that we will be seeing in the next class, next lecture. Uh, but the week 5 and week 6, week 5, week 6, I think week 7, 8, and 9 also all dedicated for turbofan. And from 10 you will have turboprop. So you will soon learn about turboprop also. There are different configurations for turboprop also.
Yes, sir.
And there is a reason to use turboprop. There's a reason to use turbojet, and also reasons to use turbofan.
Yes, sir. That I know because of the altitude traveling over there. Different aircraft are different altitude travel limitations over there. Just like you go to fighter aircraft, it's above 10,000. If you
Hmm.
go on turboprop engines over there, like Cirrus Mark II over there, best example. It's below 10,000 over there,
Hmm.
like that.
Yeah, that is one of the reasons. But you will learn more reasons to prefer each engine at a different. It's
Okay,
it's not
approaching
just the
to
altitude. It's not just the altitude.
okay,
I can give you a hint. It's not just the altitude. It is various parameters. For example,
okay.
your thrust requirements, your fuel specific fuel consumption. All these things will determine which engine to prefer. Okay, that is those are main parameters which will which will make you understand which engine is better in terms of doing this analysis. Okay, now but altitude is one of the reason, but you will have more reasons as you go forward with this course. That is one good thing about this course also.
Okay, sir.
All right. Yeah, I think that's it from my side. So the important takeaway from this is, um, we understood how to solve a turbojet engine. So I think a similar question is there for your week 3 assignment. So we found out how do we perform calculations for turbojet engine. We also discussed something about the TS diagram, and we also found exit area, calculation of exit area, thrust and TSFC. In addition, also we also discussed something related to working of each components of a turbojet engine. So in next week, what we will do is we will take this turbojet engine, we will add a afterburner to it, and then for the same question, if we have a afterburner, what are the parameters it is affecting, and why do we even need a afterburner? Basically, one, like, you will get more understanding about why we need afterburner, what is the reason to add, and also how it is physically changing the things that we will be able to see. Okay. All right. With this, let's meet next class. But if you have any questions, you can stay back and ask. I will be here until 9 o'clock. Thank you. Thank you, Tushar. Thank you, Krishna, for joining. Tushar, I will get back to you about this, about the questions that you asked, specifically the moisture content in the chamber and also the coating, nozzle coating. And also, I will talk. Actually, there is one more course that you will be, I think you will be more interested in. It's about Professor Chetan Mystery's another course, axial flow, compressors and turbine. I think axial flow, uh, some course related to axial flow. Maybe I can show it. So that, I think you will get an answer about the blades configuration. Why we need to run with a bigger. Why, what are the different technological advancements that we have for in terms of blade, you know, technology. So maybe I can show what is this axial flow compressors. With the same professors you can get axial flow compressors and fans. This is also a good course, actually. You can give it a try. Okay. I think all the lectures are already available in this website. I'm not sure whether this is available for enrollment.
Enrollment is not available, sir.
Oh,
Previous year it was there.
maybe in the next semester it will be available, I guess.
Yes, okay.
Yeah. But yeah, if you are more interested, you can go through, all the videos are already available. You can go through that. Okay. I also need to actually go through that. All right. Thanks, Tushar.
9 o'clock again we have to attend the meeting or what, sir?
Come again?
9 o'clock again we have to attend the meeting. As you said, no, 9 o'clock we will meet again.
No, no, no. I was telling, so the entire duration of this interactive session is from 7 to 9.
Oh, yeah, yeah.
So
That I already saw in mail.
yeah, I will. So I'm. So the questions I have in my mind, I completed it. So if you have doubts, you can stay back and ask till 9. I will be available.
No, no, no. Whatever doubts you already cleared,
Okay.
and now my work is to study this thing and complete the assignment over there.
Sure, sure,
That is
sure.
done.
Okay. All right. All the best, Tushar.
Thank you.
I will get
Good
back
night.
to you about the questions, huh? Next
Yeah,
week.
yeah. Good night, sir. Good night.
Okay. Good night, Tushar. Bye bye.